Exam 2 is a week from today. So that's Friday the 24th. And the topics are everything up through members loaded like stress elements. I need to come up with a better name for that. So that means there's not going to be any internal loads. So all of the new stuff that we're doing, starting right now, is not going to be on there. So if anybody has any questions related to homework or stuff that's going to be on the test, I'd be happy to answer that. We don't have school on Monday. So the only 2 days left before the exam are today and Wednesday. So if you have any questions today, I'll answer them. If you have any questions, bring questions on Wednesday and I'll be happy to answer them too. On Wednesday, we're supposed to? We should then, yeah, because we skipped the last one. Yeah, I think we should. we should, but we won't. No, that's not correct. Anybody have homework questions? Okay. So now we're going on to internal loads. Well, yeah, I mean, it's just going to be based on lecture notes, just what, remembering stuff about the lecture notes, and then possibly reproducing a problem from the homework. But it's cumulative, so it can be on anything. Yeah. So internal loads, I don't know, I think I might have drawn this picture a couple times already, but I think this is a good sort of motivation for internal load. So there's your hand. There's your other hand. And say you're holding a stick. And you're bending it. Well, the external loads, if I draw a free body diagram of the stick, your fingers are pulling down, your thumbs are pushing up. So the external loads are happening basically in 4 places, here, 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 here. But you probably know from experience that if you do this until the pencil breaks, it's not going to break at any of those 4 points. It's going to break somewhere in between these two. And so calculating just the external loads on an object isn't enough to predict where it's going to fail. And so it breaks in the middle. Because of the loads applied to points inside the stick, let's say interior points, by nearby interior points. So that's the idea of internal loads. We want to calculate the loads that are applied to one place inside a beam by the points next to it. And so I'm going to start with So we'll start with sort of a simple question and we'll work up from there. So let's say that we have a cantilever beam. So there's the wall. The beam's connected to it with a fixed joint. And let's say this is 1/2 meter and this is 1/2 meter. And let's say that we're applying a 1,000 Newton force here, where this is a 45-degree angle. And let's say also, and this is something that's a little bit new from the way we did it in statics, let's say we're also applying a couple in that direction of 5,000 Newton. That's a lot. Let's say 500 Newton meters. And we want to calculate the internal loads right at the midpoint. So what are the internal loads, or let me say it this way. What are the loads applied to the material to the left of that dotted line by the material to the right of the dotted line? Okay, so the way that we're going to solve this is we're going to isolate the left half. So free body diagram of the left half. And so here's the whole beam. But we're not isolating the whole thing. We're just isolating this. No, we can't do that yet. Sorry, that's a screw up. Erase all that or scribble it out. First, we have to calculate the external loads. Okay, so first we have to calculate the external loads applied by the wall. Okay, so free body diagram of the whole beam. So this time, over at the wall is a fixed joint. So we have a full force vector. Since we only have forces in the xy plane, the only non-zero components of this force applied by the wall are going to be an x and y component. So I'll call that RA. And then that fixed joint also is going to apply a couple to prevent any rotation of this object. There's going to be one component like this. I'll call that MR. And then there's also going to be a component in the x direction to keep this couple from making it rotate like this. So we're applying an external couple of 500 Newton meters like that would make it spin around its axis. And so there has to be a couple applied at the wall to keep that from happening. Doesn't it have to be the opposite direction? Yeah, but that'll come out. But we'll just let the math do that. So we'll just always assume it's in the positive axis direction, and then the math will tell you the direction. So over here, we have 1,000 newtons. And then we have this couple, 500 newton meters. We're neglecting the weight of the beam. And so Newton's second law says RAX, RAY, plus this 1,000 Newton force is at a 45-degree angle below the horizontal. So that's going to be negative 707.1, negative 707.1. And those are all the forces, so that's equal to 0. So this tells us that RA is equal to positive 707.1, positive 707.1 newtons. Okay, now we have to deal with the rotational equations. And we have moments happening in two directions. We have moments happening about the z-axis. That's the one that's dealt with this couple. And then we have moments applied in the x, about the x-axis. That's the 500 Newton meters and this reaction load that keeps it from rotating about the x-axis. So I'm going to break it up into two separate equations. So we're going to do rotational Newton's second law, first about the z-axis. And the moments we have MR, and then the 707.1 component of that 1,000 Newton force is going to produce a moment about the z-axis. I guess we have to choose an about point. Let's choose it right here. Okay, so this is a downward force of 707.1 with a moment arm of 1 meter. The length of the beam is 1 meter. So we have a moment arm of 1 times a magnitude of vertical force of 707.1. And then if this was a hinge, or like a pin, this thing is free to rotate around that hinge. With that downward 707, if you apply this downward force, would it rotate clockwise or counterclockwise? Clockwise. So that means this moment is negative. Those are the only two moments about z, so set those equal to 0. And that tells you that MR is equal to 707.1 newtons. And then the last thing we have to do is add up all the moments about the x-axis. And set those equal to 0. Well, I didn't give this a name. So let's call this capital T R. So that's the reaction torque. Okay, the reaction moment about the x-axis at the wall, we're going to call the torque. So T sub R plus 500 is equal to 0. And so T sub R is equal to negative 500. And so there's that negative sign that you were talking about, and it just comes out in the math. The units are Newton meters. Yeah, yep, you're right. Okay, so what we did is, and this is the answer. These are the internal loads. You're right. These are the reaction loads. reaction loads at the wall. I'm getting ahead of myself. So now we're going to isolate the left half of the beam. And so if this is the whole beam, and you have that 1,000 Newton force applied over here, and you have that torque, that external torque applied there, we're only going to isolate this much. And so let's think about what loads are applied just on this left half. Well, now we know all of these external loads. We calculated those. So we know there's a force vector applied at the wall of 707.1, 707.1. And we know that there's a moment about the z-axis of 707.1. And then we know that there's a torque in the negative x direction. I'm still going to draw my axis in the positive x direction. And then the value is negative 500. Okay, so those are all the loads applied at the wall. What are the loads applied at the cut? What are the loads applied right at the connection between the half that we're isolating and the half that we're not isolating? Well, what we're doing here is we're assuming that there's a fixed joint between, this is all solid material. And so we're assuming that there's a fixed joint between the half that we're isolating and the metal or whatever that material is that's now part of our external world. So we're going to treat this fixed joint the same way that we treated the fixed joint at the wall. Okay, so that means in order to counteract these forces, there has to be a force vector. To keep this 707.1 couple from rotating this part of the beam, we need a couple over here. And to keep this torque from making it spin this way, we need a torque on that side. And since this is a fixed joint, that joint is capable of applying all those kind of loads. So I'm going to call this force R. And then I'll call this MR. And then this torque along the long axis of the beam I'll call T, script ET. And so now if we add all these up, set them equal to 0, we can calculate those loads that are applied to our chosen part of the beam by the part that's not chosen. And notice that, so now these external loads don't show up in any of our equations or our free body diagram, because these are applied to something that we're not isolating. So how is it if these don't even come into this problem? I think this is something that's confusing for a lot of people. We know that there wouldn't be any internal loads in this thing at all. I mean, this thing would never break if you didn't apply these loads, right? So how is it that these things affect the answers of the internal load calculations without us putting them in this drawing?
Reaction forces.
Yeah, that's right. What does show up are the reaction forces. And before we isolated this half of the beam, we isolated the whole thing and calculated the reactions, and those depended on those. Okay. So that information is in the problem, but it comes into it through this. So Newton's second law says 707.1 plus Rx, Ry is equal to zeros. And that tells us that this reaction force R is equal to negative 707.1, negative 707.1. That's Newton's. And now we'll sum the moments about the z-axis. So rotational Newton's second law about z says positive 707.1 plus mr is equal to 0. So mr is equal to negative 707.1 Newton meters. And then isolate, add up all the moments about the x-axis. We have a torque of negative 500. And then the only other moment about the x-axis is this torque T. And so that internal torque T is equal to 500 Newton meters.
Why don't those MR depend on what you use?
Yeah, well, those torque calculations are not ever, those torques are not going to be provided by forces. They're just going to be applied as pure moments. You know, those are always just going to be couples. And so we don't have to worry about that. But you're right that if, like, if you thought about it this way, and you had a torque applied over here, you know what I mean? So you had a torque going that way, and then that was being counteracted by a force that wasn't all the way at the boundary of this thing. And the moment arm of that torque would be here to here. That distance would matter. You know, but we're just always, we're not dealing with forces and distances from the axis. What we're dealing with are just pure moments, you know, just couples. We don't know how those are applied. We just know that they're applied somehow. Okay. Okay, so these things. Yes. It's not massless, but we're just not including the mass because in problems like this, a lot of times the other forces just dwarf the weight force. You know, so it has a weight, but if you included the weight in, it would be small enough. It didn't really change the answer percentage-wise. You know. Okay, so these are the forces on the left piece, on the left half. Yep. Nope, it doesn't. That's just pure statics. What would change is if you applied those moments, how would it deform? You know, so if you had like a rubber beam and you applied these moments, it would twist 5 times around or something. If you had a steel beam, it would just barely twist. You know what I mean? Yeah. But you know, I said the thing about rubber. our calculations don't work for something like rubber where you have a big deformation. But for steel, where you'd have a small deformation, yeah, we can do those calculations. All right, so the next question is, what would happen if instead of isolating the left half, we isolated the right half of this beam? So what if we wanted to, what are the loads applied to the right half of the beam by the left half? And the answer is that's a Newton's third law kind of thing. So Newton's third law says those internal loads would be equal and opposite. And because of that, because we don't like the idea that this measure of the loads that are happening inside the beam depend on whether we're isolating the left half or the right half, we're going to come up with a new sign convention, a new set of variables that are independent of how we do the calculation. So to fix that indeterminacy, we introduce a new set of sign conventions. Well, just the fact that, like, if you wanted to, so what this says is, if you wanted to calculate the internal loads at the middle of the beam, you would get one answer calculating it based on the left half of the beam, and the opposite answer from the right half of the beam. So it's like, what does it mean that you're asking for the internal loads at that point? That's not enough to answer that question, and we would like it to be. We like just one set of numbers that represent what's going on at that point inside. So I'm going to introduce this new sign convention that works, gives you the same answers whether you work from the left or the right. So this set of internal loads will give the same answer from the left that will from the right. And so here is the sign convention. If you're working this way, if you're working on, if the part that you're isolating is the left, and you're calculating the loads applied to the left by the right, then the internal loads are going to be called the tension this way, the shear force this way, the bending moment this way, and the internal torque this way. And there's two T's here. I don't know, that's not the greatest, it's a little confusing, but the torque is always going to be that fancy T, and the tension is going to be the regular T. And if you're working the other way, so if you're isolating the right side and calculating the loads applied by the left side, all of these are reversed. So a positive value of tension, it would be a force vector that way. Positive shear force would be this way. A positive bending moment would be this way. And a positive torque this way.
Homework and test, would you care?
Yeah, sure, that's fine. Yep. Um, okay, so the idea is if you call tension a force going this way on on a right end of a piece you're isolating, and a force going the other way on the left end of a piece you're isolating. And if you use that sign convention, now there is a consistent answer for what's the internal load at a point. Okay, calculating it, isolating the left half and calculating using the right half would give you the same values. And so that indeterminacy is gone. The trade-off, so now these internal loads match. The trade-off is it obscures what these internal loads really are. Like the idea of an internal load is sort of a simple idea. So unfortunately, it sort of obscures the simple idea of what the internal loads are. The simple idea is that at that cut, that imaginary cut that we make, there's a fixed joint between, adjoining pieces of material. And the internal loads are just the loads applied by that fixed joint. Okay, so let me do that calculation again using this new sign convention, which is sort of it's like kind of a weird looking sign convention. I mean, I'm sure there were reasons why they came up with these, but like we're always going to isolate the left half just so that we do it consistently every time. And so I guess the weird thing is that tension lines up with the positive x-axis. That's fine. The torque lines up with the positive x-axis. The moment lines up with the positive z-axis. But this shear force is sort of odd. Like that's in the negative y direction, and that can be confusing why you do that. I don't know why, but that's just how it is. We didn't get to choose. Okay, so now let's isolate, do that problem again, do that example problem again. Using this new sign convention. Okay, so free body diagram of the left half of the beam. So I'm going to draw it like I did before. So here's the whole beam. And we're not isolating the whole thing. We're just isolating this much. And that means that we're not dealing with this force or this torque. The external loads at the wall are a force of 707.1, 707.1. A bending moment of positive 707.1, and then a torque of negative 500. And the only other loads are applied at this fixed joint between the two pieces. Now instead of representing that as a force vector and a bending moment about z and a torque about x, we're going to use that new sign convention. So the force vector is now a tension force T and a downward force V. The bending moment is like this, and the internal torque is like this. Any questions about that yet? Okay, and then Newton's second law says 707.1, 707.1 plus, this t is in the positive x direction. So think of like multiplying the variable t times a unit vector in the positive x direction. So that's t times the vector 1, 0, which just gives you t0. And now think of multiplying the variable v times the unit vector in the direction of that arrow. What's a unit vector in the direction of that arrow? Yeah, it for y, so 0, negative 1. Yep. And so the vector is 0, negative v. And then set those equal to 0. And you get that t is equal to negative 707.1 newtons, and v is equal to positive 707.1 newtons. And then the moment equation about the z-axis, we have a couple of positive 707.1 from the wall. And now, this bending moment m, is that rotating in the positive z direction or the negative z direction, according to the right-hand rule? Positive. So for that one, we just add on m. And then are there any other forces? Those are both couples, so we didn't have to choose an about point yet, but now we're going to have to. I'm going to put my about point there at the left hand. Are there any other forces applied to this member that create a moment about that left end point? Yeah, V does. And what's the moment arm for V? Yep, so we have a moment arm of 0.5 times a force V. And then if you applied that force V, it was 50 or something, if it was some positive number, would that make this thing rotate clockwise around the about point or counterclockwise? Clockwise, so that's negative. And now we can plug in, we already know what the value of V is. We calculated that it's 707.1. So this says 707.1 plus M minus 0.5 times 707.1. 353.5 is equal to 0. And then solve for M. And you get that M is equal to negative 353.5 Newton meters. And then the moment about the x-axis. Yeah, we can't do that though yet because, well, that's right. If you remember, if you take the x derivative of the moment, it has to give you shear force. We can't do that or see whether that holds here because these are just point values. Remember, that was when we calculated these as functions of x. And we'll get to that. But for now, we're just taking it in a single x value, so you can't take derivatives with respect to x. And then the moment about the x, we have negative 500 plus t is equal to 0. So that internal torque is equal to 500. Any questions about that? Okay, so these are the internal loads at a single point along the beam, or at a single x value. So these are the internal loads at a single x value along the beam. We'd like to calculate these internal loads for every x value, come up with a representation of the internal loads as you go from the extreme left end to the extreme right end. So what we'd like is to represent these represent the internal loads as a function of x. That represents every point. Okay, so can we do that with the problem we just did? Let's see what we can do. So back to the old example. So this time, here's the whole beam. Yeah. Okay. So this time what we're going to do is we're going to isolate a piece that's some unknown distance from, that's some unknown distance x long. So this distance is x. And we don't know anything about what x is except that we know it's somewhere between 0 and 1. It can't be less than 0 and it can't be longer than the beam. But no matter what this x value is, it won't get to this force and it won't get to this torque. Which way did that torque go? Okay. And so the loads that are going to be applied are the forces at the wall, 707.1, 707.1. The Z couple at the wall, 707.1. And the torque at the wall of negative 500. And then the internal loads, T, V, M, and torque. And so now we're going to calculate those internal loads based on this arbitrary distance x. So Newton's second law says 707.1, 707.1 plus T0 plus 0 negative v is equal to zeros. And that tells us the same thing that it told us at that specific point before. T is equal to negative 707.1 and V is equal to positive 707.1. And then the moment equation about the z-axis, and I'm going to use the left endpoint as the about point again. We have the couple of 707.1. We have the bending moment, m. And what other force applies a moment about the z-axis? That's right, v again. And before we knew the moment arm was 0.5, this time we're not specifying that this is 0.5 long, we're saying it's x long. So the moment arm this time is x. So we have the moment arm of x times the magnitude of force of v. And then if v was positive, would that make it rotate clockwise or counterclockwise around the about point? At v. So here's v. If that number is positive, that's a downward force. Would that make it rotate clockwise or counterclockwise around the about point? Clockwise.
You said that v was positive.
Okay, so if the number v is positive, then you have 5 or something. You have a force of 5 acting down. And so that downward force would make it rotate clockwise around that about point. So this is negative. And that's equal to 0. And so now you can plug in for v. We know what the value of v is. So we have 707.1 plus m minus 707.1x is equal to 0. And so the bending moment is equal to 707.1x minus 707.1. And then the last one is the moment equation about the z-axis, about the x-axis. Sorry, we did z. So about the x-axis, we have a couple of negative 500. And the only other thing we have is the torque T, plus T, is equal to 0. And so that internal torque T is equal to positive 500. Okay, so based on this now we have these functions that tell us what the internal loads are at any point x along the beam. The internal tension and the internal shear force and the internal torque, they don't change. Those are just constant the whole way in this case. That won't always be the case, but this is sort of a simple problem. But the internal bending moment changes as a function of x. And so based on this function, if the possible x values are between 0 and 1, where do we have the biggest absolute value of the bending moment? At 0. So what that says is right at the wall, material points right near the wall are the points where we're most concerned about this beam being broken by bending. Okay, and then that value gets, becomes a smaller and smaller negative number as you get closer towards the end. And intuitively, that makes sense if you think about this problem. Okay, so if you have a cantilever beam like this, you're applying a force here. Where are you most worried about this breaking? You're most worried about this breaking right off the wall. That's sort of an intuitive answer. So that's sort of the basic idea, and we'll just keep adding, complexity. There's about 3 steps to being able to do all these problems. Okay, that's all.